Hello and welcome to Ironville, exciting Twitch and YouTube show where we do programming, in Zeek, and where we program a distributed database for financial accounting in Zeek, and also, we do a lot of other fun things like non-relocating memory after startup, recovering from all disk faults, running distributed database with oddly sized quorums. Our quorums are even, and other stuff. And today we have actually super special episode because I am not alone here. Today we have Toby again. If you remember, Toby joined us several months ago, where we were discussing the exciting question of why Target is so slow. So in the meantime, Toby was actually investigating this question further and managed to make it quite a bit faster, and today we are going to look at one of optimizations which was discovered, and that is implementing a fancy pants K-way merge algorithm for our LSM tree called the Tree of Losers. And I will be completely sincere. I know how merge sort works. I know how to do K-way merge with the heap. But for this Tree of Losers thing, not only I don't know how it works, I have never ever heard this name. So I'm extremely curious about learning some cool algorithm here. With that, let me hand it over to Toby. I can hear you definitely, although I must say I'm not entirely sure if your audio is on the Twitch stream, which would be pretty sad if it isn't. Yeah, same here, because actually, okay, let me quickly check this, because it also isn't showing for me locally. So let's see if people in the comments hear Toby. Would be extremely sad if it's the case. But anyway, I do hope that I capture this locally. Okay, this is embarrassing. Uh, can you say something again?
Yes, test.
Okay, perfect. I think now it should work. At least people should be able to hear you on the stream. But the problem is
Perfect.
that now I cannot hear you. Okay, can you say
You
something
cannot hear
again?
me?
Yes.
Yeah,
Okay.
test.
Now I can hear you. Hopefully you can hear Toby now.
So I think I can hear myself in the Twitch. I think it should work now.
Okay, perfect.
So let me
Okay.
maybe repeat what I said. So at the end of this episode, we will learn about the tree of losers, and we will know how it works, and it will be less complicated than setting up the stream. It's actually a very simple algorithm with a cool name, but I think otherwise it's actually quite straightforward.
Okay. So could you first to warm up quickly walk me through the standard textbook keyway merge and how we are going to be faster than that?
Yes, so the idea that the thing that we want to solve is actually we have a few sorted runs. Let me draw this here. Makes it simple. And now we want to produce one final sorted run, right? Like 1, 2, 3, 4, 5, 6. And there are several ways to do this. And the first one that would be very naive is to just look into every array, right? We go through every index, the first index of each of these sorted runs. We find out the smallest one when we compare everyone to each other, and we do this n times. And this, of course, is very slow. This is OKN, and this is very inefficient. And Alex already mentioned that there is another way to do it, and one of them is the min heap. And the min heap is actually another very simple algorithm that allows us to solve this problem in O n log k. And this is actually the best you can do in comparison-based merging. So the min heap works as follows. So let us just start by drawing this min heap already. So if we create a min heap, I actually prepared the min heap before, so let me quickly draw this for you. Seven. Okay.
Yeah, that does look like a min heap.
Yes, that looks like a min heap. And there are two properties of a min heap. It's basically that we need to have this shape, and the shape must be fully balanced except for the last layer. That's the only one that can be incomplete. And that means that every node has two children. And the only exception is, as I mentioned, the last layer. And the second one is the invariant that the parent, should not be greater than the children.
Yeah. So by induction,
That's
we'll have
basically
the smallest element on top.
Exactly. And now the question is, if you delete one, what happens? So as I mentioned, we want to produce these sorted runs, right? 2 would be our first element that we take out of this min heap. And this is also the smallest element that we have in our collection of sorted runs here. And so 2 will be the first one.
Let me quickly clarify how that connects to sorted runs. So I guess the number of elements in our heap is going to be equal to the number of sorted runs, right? So actually, in our picture, we have 3 sorted runs. So our heap actually is going to be with 3 elements.
Yeah, exactly. So
okay.
Actually, I should have drawn.
So it is not. Yeah. Okay. Yeah. Now this looks correct to me.
Exactly. So that's a good point. And what happens now? So now we need to find the next smallest element. And how that typically is done is we first fix the shape of the tree. Like I mentioned, we have these two requirements. The shape must be good, and the second is the invariant must be satisfied. Variant. And here the shape doesn't look good, right? We don't have a root node anymore.
Yeah, I mean, it's not even a tree. It's like a forest of 2 trees.
Exactly. It's and not even connected. So now to solve the first one, we just move this tree, this node up. So we don't care about the invariant first. We just fix the shape. That's the first thing we do.
I mean, it kind of like, but like, why are we moving 11 and not 9? Like it.
We can also move 9. We can actually choose.
So we could choose any node from the bottom layer. Okay, yeah.
Yes. And now we need to satisfy the invariant. Now 11 is our root node, which doesn't satisfy the invariant that every child must be smaller than the parent. And so now what happens now is basically we need to move this down and compare the root node with its both children's. And we find the smallest one and propagate the smallest one up again. Right?
Yeah,
so
basically
we swap
11 and 3. Oh, yeah. I guess it's right.
Exactly. So that's the root node now. I mean, it's going to be ugly, but since the picture develops, I hope it's still fine to understand. Right, so we have shifted the 11 down, now 1 level, and we have the 3 up. So the 3 is actually quite nice because this is indeed the smallest node, but we still need to deal with the invariant. So now we need to compare 11 with 6 and 5, and we move 5 up and move 11 to here. And that's basically the final replacement for the first pop that we did. And now we do this again, and we get the 3, and so on and so on. And the most important part that I want to highlight here is that we always push the element that we replace the root with down. And for that is we need to compare 2 nodes. Right? We always need to compare the left and the right node of our children and take the smallest one.
Yeah, because we don't know which child is smaller.
Exactly. So typically we have 2 log 2 log k comparisons. So the runtime is n log k, but in terms of comparisons, we always have 2 log k in the worst case.
Because and I guess like our the node, because we picked it up from the like bottom of our tree, it actually like it is not guaranteed to be like, you know, super heavy node, but probably it will sink like to the very bottom.
Yeah. It can stop a bit earlier. Like here we had now 1 layer up, the 11, because we were not complete here, but it sinks relatively deep. Exactly.
Yeah.
And so, as I mentioned, n log k is basically the best we can do with comparison-based merging, but we have 2 log k comparisons. And this thing that we can actually improve with the tree of losers.
Okay,
because the tree of losers only leads log k comparisons. And the tree of losers is actually very cool. It's very simple. That's why it's cool. It's very simple to implement also. I can later show a bit of the code. So let's imagine we have like 4 sorted runs. Again. Now I draw them
vertically.
From top to bottom, exactly, vertically. So we have 5, 10, and we have 3, 6, and 4, and 8. Okay, and since we again want to do n log k, that means we again have a binary tree at the end. So basically we again want to have this log k property, so we need to get some tree shape. And how we initialize the tree of losers is actually we let them compete against the neighbors, like here 2 and 5, and choose the one that loses. and the loser is stored here. And we remember the winner now for the next round. Let's draw it here. That's only for the initialization. And we compare here on the right side, the 3 to the 4, and the 4 is the loser here. And it's called loser's tree because it's a tree full of loser. Like a tournament tree, there's also a winner tree that is similar to a heap, but the loser tree is basically storing all the losers. And so we have now the 2 and the 3 that go to the next round, and they compete again. Let me draw here the binary thing. And here the 3, of course, loses, and the 2 wins. Oops.
Oh, okay. So this is subtle. So on the first round, we say, okay, loser is 5 and 4. And I would naively assume that the next thing is like, we'll going to make losers compete with each other, but that's actually not what we do. We actually like make other folks compete. Okay, yeah, now it makes sense to me.
And this is the initialization step. That was basically now the first competition where we needed to compete the neighbors. But now the nice thing comes when we want to, so we have the 2, we get the 2 out. Now we want to get the next winner. And to get the next winner, we need to remember, that's what we also store in our data structure, where the winner came from. So it came from batch 0. Let's also draw it here. These are the number or IDs of the batches. And typically they are also stored in these nodes themselves with the either a pointer to the value or the value itself. It depends on how big the values are and such. But we always need to know where it came from, like the identity. And so the first value, the first winner came from 0. So now we take the next one from batch 0, which is the 7. And now we only need to follow up this path. So we compare the 7 against the 5, and the 7 is the loser. Now we have the 5, compete the 5 against the 3. The 5 is the loser, and the 3 is the next winner. And the 3 originally came from batch 2, from here. So I will make it one more time, and then maybe Alex, you can do it. It's very simple. Right? We remember here the.
I think you're setting me up because I think the case you have showed is actually the easy one because, like 7 replaces 5, and then 5 replaces 3, and then 3 is a winner. But what happens if
they actually? Let me do 2 more.
Okay.
So we have the 3 that was the next winner, right? We have it from batch 2. So what we do here is we take the 6. We compete the 6 against the 4. The 6 loses. The 4 is taken up. Now we compare the 5 against the 4. And now is the case that you mentioned. The 5 doesn't lose. And the 4 is just propagated to the output. So it's basically just a simple one-to-one comparison. And whoever loses will be left in the tree. And whoever won goes 1 level up. Okay, so let's do one more. Right, the 4 came from 3. So we do the 8 now.
Okay. Let me do it.
Okay.
I believe in myself. Okay. So we follow the path up the tree. Okay. So we compare 8 with 6. 6 is smaller. Being smaller is good. So 6 is a winner and 8 is a loser. So we move 6 one up, and now we compare 8 with 5. And now 6 is a loser, so we swap it with 5, and 5 is the new winner. So the next answer is 5.
Exactly. Very good.
Okay. But why does it work? I mean, like...
Yeah, that's actually... So there is a very long chapter about this in the Knut. I think Knut has everything, and for everything is the long chapter in it. And it's basically basically the observation that if you can do a leaf to root traversal, you only always need to compare once. And to achieve this, you need to save the loser information, because you know that when you pick the next one from the winner's batch, then on the way up, you will find the loser that is propagated most up, and then that will be the next winner, if it's not from the same batch. Because you know that if one of the element came from a batch, it could be that the next element is the next one that is only one element larger for integers. And so we definitely need to take it from there, and then we propagate it up all the way, and we are basically guaranteed to find the next element on the path from the previous winner.
Okay, so okay, let me try to understand it. So okay, we know the current winner. The current winner goes away. We pick the next competitor. Like we haven't looked at it before. We know that it is larger than our previous winner, but it can still be smaller than all the previous folks. So we make we make this new element compete with everyone else who was fighting against our previous winner. And if a new element wins in every round, that means it is still the winner, and that means that like, hey, we still it is still the minimal element. Because yeah, like we know that like the previous winner was a winner because it won over everyone else, and the new one also win over everyone else, so it's also good. Okay, so this case I understand. Now like the and again, as I've said, like this is the easy case. Like you just like well actually this is. I think this is like the hard case where like like you are like going to propagate it up. But now what if we okay, no, I understand. So let's say that like on some round, like our new element actually lost. It is now a loser, and the new winner is the element which previously was a loser. Well, then we make that X loser compete with everyone else, and kind of like that works out recursively. Okay, so okay. I think I'm not quite ready to like write a formal proof with induction and whatnot here, but I think I convinced myself that this basically works.
Yeah. So one thing that we need to, so maybe we should provide a bit more context for why we want to have such a thing. So of course we have sorted runs, and we want to produce one sorted run at the end. What we currently do is we just sort all the sorted runs again, like we have them pre-sorted in one big array, and we just throw on another sort. And complexity-wise, in the worst case, this is n log n. So it should be, at least complexity-wise, it's worse, right? But since the merge sort can exploit the fact that these things are already pre-sorted, it's actually, in terms of performance, it's not so bad. But we want to get it faster because this causes some latency spikes that we would like to get away. And Zig's sort is a stable sort. That means that when we have a 2 here and another 2 here, and they are attached with some, say, value, so this is the key and we have a value, then in the final sort, we want them to be ordered as they have been in the original order of the sorted runs.
Yeah.
And this is important for us because we want to, or we need to, deduplicate certain elements. Some of them are tombstones, and so the order in the way they came in, they are quite important because we then only need to maintain the last one that is there if they annihilate, for instance, each other. And the tree of losers initially, like the normal algorithm, the plain algorithm, is not stable. But it's very easy. It's very easy to add a tiebreaker, and the tiebreaker is just the batch ID. So if you find a key that is equal to myself, then I need a tiebreaker, and that is the batch ID. So we just need to make sure that the way we enumerate the sorted runs for the final loser tree are also the way that they were produced. Like 1, 2, 3, 4, and then we have a stable replacement of this initial sort that we do.
Okay, yeah, this is perfect. But before we move forward, can I ask like a stupid question? Like, I mean, if this is faster than binary heap, then like, why do we need binary heap? Or well, wait, actually, I guess like this actually isn't a heap, right? So like, I cannot like just take a bunch of elements and throw them into a tree and make it heap, or can I?
I think you could, right? And actually, a lot of people do K-way merge with MinHeap.
But I'm not. I'm not thinking about like the K-way merge here. I'm now thinking about like other uses of heap. Like I don't know, like for timers. Like I have an API for like ARM timer, an API for tick time, and API for like fetch like all the timers which are expired at a given moment. So like the simplest way you can do this like without timer wheels is just like throw all the timers in the heap. Like, can I do this with a tree of losers? Or is it?
I think so.
Huh.
I think so, actually. I've never thought about it because I only know it in this K-way merge kind of scenario. But I mean, somehow you're right. It somehow feels not
like
not as well suited.
Like, were we lied to? Like that's like you should learn like binary heap. Like you should maybe you should do this thing. Like maybe there shouldn't be like heap sort. Maybe we should be using like loser sort, which is not the most.
There's actually an
exciting
algorithm that's like the loser sort. I mean, it's not called loser sort, but it loses the tree of losers internally.
Okay.
I think it's called.
I understand the reason why it's not called that way.
I actually wonder now your use case. But I think it should work. The only thing is that you need to somehow. I mean, or let me phrase it differently. If you have a bunch of timers that are already there and they have pre-sorted, then it works, right? If they are just random, then we have an issue.
Oh, because there is no insert operation here, right?
Yes.
Oh, okay. Yes. Okay. Yeah. This is the thing. Like we cannot just incrementally insert on this thing because like that breaks the whole tournament.
Yes, we need to have the sorted batches beforehand.
Okay. Yeah.
Or if the timers are naturally occurring in a sorted stream, then it also works, right? So you don't need to have all the values already, but they need to have the property that these things are naturally incremental, monotonically increasing, at least in some form or way. We need to have this property.
Yeah. Well, I'm still amazed that I haven't heard about this. Like, I mean, I've heard about like binary heaps, like K-way heaps, like Fibonacci heaps, like whatever. But I mean, this is like super simple, and it feels like everyone should know this algorithm. Okay, can we look at the code? I bet the implementation also can be pretty simple.
The implementation, if you do it naively, is actually also very simple. But also let me insert here a warning. The code is not really very nice that I hacked together. It is more like a prototype thing.
Okay.
I need to figure out how I can share it now.
Yes, because I think what I'm seeing right now is black screen. So unless you are using very dark theme with like very dark font, you're probably not quite sharing your code yet.
Not yet, no. It's like technical problems.
It's kind of like
so here
looks pretty much like Malevich. Okay.
All this code that you see now is actually basically just benchmarking stuff.
So like, can we make font size like 10 times bigger?
Big?
Like a lot bigger. Because
like this?
The quality.
And let me share it like this. because otherwise I
Well,
can't see the code anymore. Is this big?
Okay, it is big enough. Like the quality is like super horrible, but I think I can manage.
Is it now better?
I mean, now it just got completely. I'm seeing black screen again.
Okay, that's not good. Then let me revert this again. All these technical challenges.
Yeah, I mean, like how many database developers do you need to share screen?
So the tree of losers definitely is easier than this stuff here, right?
Yeah. I mean, maybe it is also easy. It's just that we are not good at streaming. But well, that's why we are like database developers and not like YouTube stars.
Do you see it now?
No. Still blank screen.
Why? Now you see it again, right?
Yeah. I can see it.
Okay, now I need to make it bigger again.
Yeah.
I think.
Yeah.
Like this?
Yes. This is like roughly visible.
Okay, so ignore all this stuff here now, and let's only focus on this next call. The next call does basically exactly what we played through. It takes basically the batch ID from the previous winner. So we have a variable where we store the previous winner in, and we get the batch ID. And we basically just increment the index into our sorted runs.
Yeah.
So we get the current position. We check if the current position or if the current sorted run is already exhausted. If it's exhausted, then we do a sentinel value.
Yeah.
And here it's important that we have some key that is actually big, but also this could be occurring naturally in the sorted run. So we need to also set the batch ID to K. And because we have K sorted runs, but they start at index 0, K is basically will not be available. We could also make this super high, like K max or something. But exactly. Yeah. If the sorted run has actually elements, then we just store it in our temporary variable that we call winner. But this is not yet the winner, right? It's just the current competitor that we need to determine if it will be the winner. But we use this variable to store the next winner. Like if it loses, then we store the new winner here. So then we go over the height, like from the tree leaf to the tree root, and we calculate the parent ID. And the parent ID, when you remember from the sketch that we had before, the parent is basically the loser of the previous runs.
Yeah.
Exactly. So we compare the current value that we have here in self winner against the current loser that has been left in the tree node that we calculated here with parent ID.
Quick question. Like, could you explain a little bit how we initialize parent ID at the beginning, like self tree land plus batch ID?
Yeah. So this one. So the layout that we have for the tree is essentially similar to I think Etzinger layout, and so you can simply allocate it in a large array and then calculate it with some formula. And the initialization is basically our own value. Basically, that's the first batch where we are actually in, and then we calculate the parent by dividing it by 2 minus 1.
That's okay. I'm still kind of like confused because like our own position is batch ID, right? Why we also add tree land there?
That's just some artifact of the code. It's basically because what we have is the root is at position 0. Then we have the 2 next children. So the left one.
Okay. I think I got it. So it's basically kind of like shifted by like
Exactly. And that's why the tree lane is actually the real data structure that we have. That's why we added by this tree lane thing, because at the end then we have here the temporary for batches.
Yeah. Oh, actually, I think this is another case where this is different from binary heap, because like in a binary heap, we like organize the elements themselves in a tree. So like the size of a tree is exactly the number of elements. And here, like we make the tree twice as large because you need like the tournament. Okay, yeah, that makes sense.
So the tree is actually only k large.
But like, I mean, isn't tree.len?
So basically, you have k leaf nodes and then the inner nodes.
Yeah.
So the formula is actually somewhere here.
But I mean, if you have k leaves and then inner nodes, then the total number of nodes in the tree is actually 2k. Because like half of a tree is the leaves, and the other half of the tree is everything else.
Yes, but the leaves you actually don't need to store, because they are already given by the sorted runs. So each element in the sorted run that we're currently at is essentially the leaf. And this calculation, if we would go to this index, we would get an index out of bounds, because that's just a virtual index where we would have the leaves if we actually would store them. But since we store them in the sorted runs.
Okay. Now this is clear. Okay, thank you.
Sorry, sometimes that I wrote this code. So this is also very badly named, because this is not yet the parent ID. It actually only becomes a parent ID here. This is actually the would-be leaf ID, but it's we don't actually them.
Yeah. I think we could call, I think like, there is a winner, but like right now the thing is a challenger. So this is kind of like challenger index. Yeah.
Challenger is actually nice. Let's remember that, because actually I want to revert some stuff here and show the problems that we will encounter soon. So basically here we just compared and see if the challenger is greater than the loser that has been there in the parent before, has been left behind. If it's equal, then we need to do the tiebreaker. And here we just check if it's a new winner. And it's a new winner. We have a new winner if it's larger or the tiebreaker was basically true. So we had a tiebreaker and we broke the tie. And then we swap it. And then we return this is also not super meaningful, but we return the next winner.
Okay.
And that's basically this loop is the hot loop that we do height times. Okay. And the challenge is, unfortunately now, I mean, it sounds super nice and you understood it now. It's pretty cool. But one question is now, how fast is it? And this is now very annoying to read. I actually don't know if I can make this like so. Can you still see it?
Yes, I can still see it.
Okay, so here we compare the loser tree with the STD sort, and the workload is basically very similar to the one that we see in Tiger Beetle. So it's a kind of micro experiment. And what we can see here are multiple things. So first, when we look at the pure runtime, then we can see that the loser tree is actually slower. And the baseline is basically we have these k-sorted runs already pre-sorted and we sort them again. That's how we do it currently. So what we measure here is only the final sort, like sorting the k-sorted runs.
Yeah.
And it turns out the STD sort is actually faster. And when we normalize it by the number of elements that we merge, then we see here a few interesting things. So we see the CPU cycles per comparison, not comparison, per element that we push or want to merge. It's rather the correct thing. And we can see that of course, the STD has a lower because also the wall time is lower. That's why it must be lower. And interestingly enough, it generates quite a bit of instructions. And this is, for such a simple code, it's not really very intuitive why this should be the case. And this is the thing that I looked at first. So because I think this could be much faster, And I will show you that it's actually true that it could be much faster. And also from the code that we have, it seems a bit weird that we have so many instructions. We can see a few other interesting things that we can look soonish. So let me actually already highlight what's going to change, and then I will make the change. This one, the std memswap, generates very inefficient code for our swap here. And it's interesting because the node itself is actually a very simple struct. It only contains the key, it contains the batch ID and some padding, which is not really necessary, but I don't want to have like artificial padding that is invisible from us, so I just padded it to cache line size. But essentially it has only key and batch ID. I also removed the padding, it doesn't really change anything.
I think you can.
So we have the batch ID and the key.
I think you can make batch ID U32 rather than U size, which is U64.
Yes, that I could also do. It also doesn't change much, but I should do it. That's a good point. But let me show you the magic.
Yeah.
I prepared something here. Let's see if it works. So right, this has now changed. We had this std memswap thingy, and now we do this very crazy thing where we swap each of our struct fields manually. Yeah. Which is somehow insane. But interestingly enough, compiles a bit long, but it generates less instructions.
And now
it's faster. It also generates less instructions, but it's still not really convincingly super fast. But we can do it faster. But it's interesting that, so I want to look deeper into this instructions thingy and understand where exactly it generates so many instructions if I call std memswap.
Yeah. I wonder if this might be some kind of a safety check on the Zeek side, although...
interestingly enough, this I can also show you. If we compile it with fast, then many of the safety checks go away. The code actually gets worse, at least in the final version. I haven't checked it in this intermediate version. No, in this version it gets better. Okay, forget what I said. But let me go back to this one. It didn't compile now. I think it has cached it.
Yeah.
But it doesn't really matter. What we still can see here, we can see, okay, we are a bit faster. We have less instructions now, but we have quite a few branch misses. And it kind of makes sense, right? Because we have these k-sorted runs, and this time we have 32, and log 32 is 5.
Yes.
Right? Okay, so we have 5.
On the base, but if the base is
2,
log 2,
it is 5. Binary. So we have 5 comparisons when we do from leaf to root traversal. And since we have basically random data, it cannot predict it, right? So we have exactly, or more or less exactly, 2.5 branch mispredictions.
Yeah.
And every branch misprediction costs us like 20 cycles, roughly speaking. And so we lose, because of the branch mispredictions, we lose kind of like 40 to 50 cycles.
Yeah.
So now what we're going to do is we convince the compiler to generate branchless code, which is always a bit tricky. But let's try if we can get it.
Let's try.
It's this one. So right, we had this if here. Now we just do this crazy thing. We have an inline if where we just return the pointer to whoever is now the new winner. So if we have a new winner, then we take the one that has been placed in the tree itself. And if it's the old winner, then we still keep the old winner and we still have the pointer to it. And we just do the crazy swap all the time. Or even if we don't need to swap because nothing changed, we just swap it. because we
Yeah.
will get the self winner, and then we swap the self winner with basically itself, and everything is unchanged.
Yeah.
So, and now the code starts to look a bit more crazy, but unfortunately it also gets faster. So the question is now, do we keep the ugly code, or here I have more experiments, but let's focus on the first two. Now it's significantly faster, and we can
Yes.
see,
It's like
and
twice
we
as
can see
fast.
that the branch misses. Exactly, and we can see that the branch misses are going away,
Yeah.
which is good.
Yes.
And we actually saved more or less exactly what we calculated. We saved like 40 cycles or something. So this is good.
Yeah.
Are you
Yeah,
happy? It can actually get fast.
Really?
Yeah. So there's one more trick that is always like tricky to explain, but let me try to explain it. So what we can see here, and this is more like thinking hard and also trying a bit more, because very hard to see from these performance counters. But it would be nice if we wouldn't have so many cache misses. There are already actually not so many, but the question is, can we get them smaller? And like from the way we think about this tree of loser thing, we actually only need 32 cache lines plus the inner nodes that are also in cache, in CPU cache, always in the cache. And the sorted runs, every sorted run individually advances sequential. So it should be a very easy pattern to predict. But unfortunately, it's not, because the sorted runs advance like kind of randomly, like in random order, but sequentially. Like every sorted run individually advances sequentially, but it's not clear which one will advance sequentially. The prefetcher for the prefetcher, the hardware prefetcher, it's basically random.
Oh,
which
okay.
is very unfortunate.
Yeah. I see. So, like, it doesn't know that there are 32 runs. So, from a prefetcher, just basically read, like, random points from our array.
Exactly. So what we can do is we can do manually prefetch, and this is a bit crazy because we also don't know which one will be advancing next. So we always prefetched just the one that was the current winner. It could be that it's actually not the one that is advances, because we need to prefetch in the future. So we need to prefetch the next cache line already. And it could be that the next cache line is actually not needed since some time. But we have a good chance that eventually it will be needed. So we just do this opportunistically, and we hope it will work out. And it gives us a bit more. It gives us a quite okay reduction. It's not like amazing, but it's visible and measurable. So it's like from 92 cycles, I think it went down to 77. And so now we have more cache misses. And this is a bit confusing, but these are cache misses that are not stalling. So because the prefetch instructions, we do like crazy prefetch, we just prefetch everything. And some of these will not be in cache already, or we prefetch them twice, and they have been evicted in the meantime. We have actually more cache misses, but we don't need to wait for the data. They are loaded in basically asynchronously.
Wow, this is brilliant. Like, you
this is
are
crazy stuff,
reducing
right?
cache misses by making more cache misses. This is
only
pure,
actually, yeah.
This is
Let me
pure
preface
black
this.
performance.
These prefetch instructions, they are typically, you shouldn't. It's very often you shouldn't use them. There are only very special cases where you should actually use them, and here we only use them because it's a very tight loop. And we know that we don't destroy our caches for other work, because we will be in this hot loop for some time, actually quite some time, like 30 milliseconds. So we are not worried about destroying other caches. But if we would use this, for instance, in an iterator way, where we do other work outside and we advance only one winner always, and then we do other things, then these prefetches can be very dangerous. So we should always measure things. And prefetches in general, I would like to change the access pattern rather than do prefetches, but it's very hard for this tree of losers. We cannot change it easily. So we cannot help the hardware prefetcher to figure it out on its own. We just need to do prefetches. That's the only thing we can actually do.
Yeah. Okay.
But the interesting thing, let me show you what I wanted to show before. One other interesting thing is, it's very hard to convince this compiler to leave this code as good as it is. Because sometimes we now compile with released fast, which normally should make things faster.
It actually gets worse. It's fast, yeah.
Yeah, but it's good because, I mean, in TigerWheel we use safe. And if safe is faster, that's actually nicer. So here in this case, the safe version is actually faster than the fast version. I have a small chat with Andrew next week, or it's planned at least. I hope it, and we want to look a bit into this.
Yeah.
Because I would like to make it more stable. The other downside with such highly optimized code is that if you make any changes inside this code, it could be that the performance is again degrading. And so we need to be very careful if we do, like, we need to have micro benchmarks in place.
Yeah, which you currently don't have. And actually, like, we are soon going to upgrade to Zeek 0.14, and that actually could append like the whole thing here. So
hopefully it does things a bit nicer, because we, for instance, have branch hints in SIG 14, and I hope that I can replace this crazy thing and make it more stable with branch hints. Hopefully.
Yeah.
I haven't tested it. But yeah, so the end result is actually a bit more than like 2.3 or 2.4 times faster than the current sort.
Okay, this is brilliant. I mean, I've learned a lot. Like this is super cool stuff. Okay, but I think we are roughly at an hour, so perhaps it is time to wrap this thing up. What do you think?
Yeah, actually, I'm very tired. I'm a morning person, so I was awake since, I think, 4 a.m. And now it's like 8 p.m.
Yeah. Sorry about that. So, in the interest of giving Toby enough time to sleep, let's call today now. I don't know about you, but I'm like super excited about everything I've learned. Like, I mean, it's crazy. I've learned like both like high level like big O algorithms straight from Knuth, and also like this like low level like cache misses, branch predictions, optimizations, which is like completely crazy. Which is like simultaneously higher and lower than the level of abstraction I usually operate at TigerWheel. So hope you enjoyed it as well. And if you enjoyed it live, then perfect. If you didn't enjoy it live, then don't worry. As usual, the recording will be on YouTube very soon. And you can always join us next week at 5 p.m. UTC on Thursday, live on Twitch, where we'll be discussing something exciting again. Okay, thank you for watching, and goodbye.
Bye.
Let's hear our outro. Bye.